Have you ever walked into a supermarket and found yourself overwhelmed by hundreds of products? Now imagine trying to make sense of over 100 different chemical elements, each with its own properties and behaviors. Back in the early 1800s, only 31 elements were known. But by the year 1865, that number had already doubled to 63. Today, we recognize over 114 elements, many of which are synthetic, created in advanced laboratories. With so many elements to study, understanding them individually became almost impossible. Chemists needed a smart way to organize their knowledge, a structure that would help them identify patterns, predict new discoveries, and make chemistry more manageable. That's how the idea of classifying elements began, to simplify, organize, and even forecast the behavior of substances that make up our entire world. Let me ask you, what's the point of grouping elements at all? Well, classification in chemistry is all about spotting patterns. Just like you sort your clothes by type or color, scientists wanted to group elements that behave similarly. Classification gave chemistry a structure. It let scientists relate one element to another based on properties like reactivity, valency, and bonding type. More importantly, it allowed predictions. Imagine knowing about a missing piece of the puzzle even before it's found. That's what classification enabled. For example, it could suggest the properties of an element not yet discovered simply based on its position in a logical sequence. This scientific foresight turned the periodic table into a roadmap, not just a list, for chemical understanding. The journey of classification began with some interesting, and sometimes flawed, ideas. In 1829, Johann Dobereiner grouped elements into what he called triads, 3 elements where the middle one had properties and an atomic mass roughly in between the other 2. A classic example: lithium, sodium, and potassium. Atomic masses 7, 23, and 39, sodium sits right in the middle. Though insightful, it didn't work for all elements. Then came John Newlands, who noticed something musical. In 1865, he proposed the law of octaves. He found that when elements were arranged in increasing order of atomic weights, every 8th element shared similar properties, just like musical notes in an octave. But this law failed beyond calcium and was dismissed. Still, these early efforts paved the way for the revolutionary breakthrough that followed. And that breakthrough came from Dmitry Mendeleev, a Russian chemist with an incredible vision. In 1869, he arranged elements by increasing atomic weight, placing those with similar chemical properties into vertical columns. He gave us what is now known as Mendeleev's periodic law. The properties of the elements are a periodic function of their atomic weights. But here's where it gets really exciting. Mendeleev wasn't afraid to break the rules. If an element didn't fit the pattern, he placed it where it made chemical sense, not just based on atomic weight. He even left blank spaces, predicting the existence of elements yet to be discovered. For example, he predicted the properties of gallium and germanium long before they were found, calling them eka-aluminium and eka-silicon. When these elements were later discovered with almost exactly the properties he had forecast, Mendeleev's genius was undeniable. His periodic table wasn't just a chart, it was a prediction machine. As science progressed, so did our understanding of atoms. In 1913, Henry Moseley changed the game. He used X-ray spectra to show that atomic number, not atomic weight, was the true basis for organizing elements. When he plotted frequency of X-rays emitted by elements against their atomic numbers, the result was a straight line, not a random scatter. This led to the modern periodic law. The physical and chemical properties of elements are periodic functions of their atomic numbers. This corrected Mendeleev's mismatches and finally explained why iodine, though lighter than tellurium, belonged in a group with chlorine and bromine. Today, we built our entire periodic table around atomic numbers and electronic configuration, tying the layout directly to quantum mechanics and the behavior of electrons in shells and subshells. So, why does classification still matter today? Think about how we teach or learn chemistry. Without the periodic table, it would be chaos. Classification makes it possible to study trends in reactivity, bonding, valency, and atomic size across groups and periods. It helps students quickly identify which elements behave similarly and why. For researchers and industry, the periodic table guides the synthesis of new materials, the design of medicines, and the development of technologies like semiconductors and batteries. Even the periodic trends, from atomic radius to ionization energy, make perfect sense once elements are classified properly. In essence, classification has become the backbone of modern chemistry. Let's quickly revisit what we've explored today. The classification of elements became necessary as their numbers grew, making individual study difficult. From Dobrynin's triads to Newland's octaves, early patterns gave way to Mendeleev's visionary periodic law based on atomic weights. And finally, Moseley refined this with atomic number, giving us the modern periodic law and the long-form periodic table we use today. Classification allows us to predict, compare, and understand elements based on electronic configuration, valency, and reactivity. It's not just a tool, it's a lens through which we understand chemical behavior across the universe. I hope this session helped you appreciate how the simple act of organizing elements became one of the most powerful ideas in chemistry. Until next time, keep asking questions and let chemistry help you find the answers.